Well, and to wrap up chapter 7 and just focus more on like I said, the concept of probability, what we want to do is just remember anytime you think of probability, think of part out of whole. What are the odds that out of, let's say you have a class of 30 people, what are the odds that you're going to be selected? Well, you're one person out of 30, so 1 out of 30. What are the odds that you're going to win the lottery? There's only one winning ticket out of the million of tickets. That's all about the odds. It's always part out of whole. So looking up here, the word experiment is used to represent any random process where the exact outcome is not known, but the potential outcomes could be found. So, like, for the experiment is we don't know who's going to win. All we know is going to be one of the 30 of you guys that I'm going to select. We don't know the exact, but it can be 1 out of the 30. Okay. The set of all potential outcomes is known as the sample space. So if the sample space is an example of me just choosing one of you guys to use, the sample space would be involving all of your names. Okay. I don't know which one I'm going to choose. All I know is that only the 30 of y'all have the potential of winning, or of me selecting you. Okay. And if an experiment consists of rolling a die, so then the possible outcomes when you roll a die are just going to be the 6 different sides, right? You can get a 1, 2, 3, 4, 5, or 6 dots. If an experiment consists of flipping 2 coins, then here are the possible options. You can get 2 heads, 1 of each, or 2 tails. So those are the potential options. Again, it's not known which one's exactly going to occur, but we know what the potential outcomes are. And that's what the whole basic of probability is that we can list off the outcomes so we can narrow it down to which ones might be chosen, or the odds of something being chosen. Okay. More kind of definitions as we look to this. An event is any subset of the sample space. So it's denoted by E. It's any one, like the 2 H's. That's an event. Me rolling for example, in rolling a die, E could be 1, 3, and 5. So the event is that you're getting an odd number when you roll. The event could be when you flip 2 coins, and getting at least 1 head. So I can get 2 heads, or I can get 1. Okay. So it's almost like, think of it in out of the whole sample space, an event could be just a subset of it. If the sample space is our class, let's say our class has 30 people in it, and a subset of it could be, or event could be me picking a girl, so it'd be a separate group that has all the girl names in it. Or it could be me selecting somebody that was born in January, so that would be a specific event, a different event among the subset, or the sample space, I'm sorry. Okay. And if S is the sample space of an experiment that has equally likely outcomes, so the odds of when you flip a coin, that nothing's weighted, so the odds of you getting a 1 or you getting a 5 are going to be the exact same. When you flip a coin, getting the head or the tails, nothing's weighted, so it's going to be the exact same odds. That's what we're talking about here. So if it has equally likely outcomes and E is a specific event, then the probability of that event is right here. The probability of any event E occurring is going to be the number of ways that E can occur. I've kind of written it out right here. The number of outcomes for E divided by the total number of outcomes for the experiment. And a lot of this was a kind of formality. Just, you can read through it a couple more times, just pause it, or you've got the notes in front of you, so kind of just read through it a couple more times, or we can just hopefully look at some examples and it'll make a little bit more sense. Here in example 19, you have an experiment. It's going to consist of rolling 2 dice. What is the probability that the sum of the 2 dice is equal to 5 or greater than 8? Okay, these are 2 individual events. An event is going to have a sum equal to 5. Another event is going to have a sum greater than 8. So the sample space, the overall what's occurring here, is rolling 2 die. And then once you roll those 2 die, we have to add the tops. So here's the easiest way that I can think about it is let's draw ourselves a little chart here, where 1, 2, up here on the top are all the different outcomes I can get from that first die when I roll. Okay, what's going to be down here on the left are all the different outcomes I can get when I roll that second die. So let's pair them up. If we want to kind of write it like this, let's do a table. So I can get 2 1s, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 5, and then a 1 6. Okay, so to spare you guys some sanity, I'm going to pause this, fill this in, and we're going to come right back real quick. Okay, so just listing this out, if I go right here to this third row, first, so 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. Okay, so let's go to part A. Part A says, I want to know what is the probability that the sum of the two dice equals 5. So we can get a 5 when we do 1 and 4, 2 and 3, 3 and 2, and 4 and 1. And that's pretty much it. So out of all of these possible outcomes that are listed in here, I can get a sum of 5 4 different ways. Well, part of that definition, if I come up here real quick, it says the probability of something happen is the number of outcomes for that specific one. So the number of outcomes for me to equal a 5 divided by the total number of outcomes in the whole experiment. Let's go down here. Oops. The total number of outcomes. What's all these numbers listed here in the chart? Well, there's 6 by 6, so there are 36 total ways. And if we reduce 4 out of 36, it's 1/9. And if we choose, we can leave our answer like this. It's totally fine just to say it's 1 out of 9. Or if you want to put this in your calculator and round it out, it's basically 0.111 repeats, or 11.1%. Okay, so what that means is when I roll 2 die, the odds of you actually getting a sum of 5 is only 11%. So let's go to this next part. It says, what is the odds that you're going to get a sum that's greater than 8? I'm going to interpret that as meaning we can't equal 8, so just strictly greater than 8. So that's going to come with 9, which is 3, 6, 4, 5, 5, 4, and 6, 3. 10s, right through there, 11s, and 12s. So it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 ways I can get a sum greater than 8 out of the grand total of 36. So if we choose, if we want to just kind of type this in our calculator, if we want to get a decimal, it's 0.2777778, or you can say 27.8%. And look, that's a little bit higher, but it kind of makes sense because we're not talking about just exactly 5. We're talking about a sum greater than 8, so 9, 10, 11, or 12. So we have more options with that one. Okay, but that's how you do probability. It's always part out of whole. How many ways can I get this small thing, let's say specifically getting a sum of 5, over the grand total out of all of these total number of sums? Well, moving on to example 20. We have an experiment that's consisting of drawing 3 marbles. So again, we're going back to the marbles. We're going to pick 3 of them. That's good to know. We want to pick any 3 marbles from a bag that has 4 red, 3 white, and 2 blue marbles. What is the probability that the 3 marbles drawn are all going to have the exact same color? Okay. We might just kind of start this one out by just writing it out in words. So if we have to have we're going to draw 3 marbles and they have to have the same color. That means I can get 3 reds, or I can get 3 whites, right? I can't exactly get 3 blues because there's only 2, so there's no way that's going to happen. So how I'm going to get 3 reds, specifically in the experiment when I want to draw 3 marbles, so I'm going to do a combination because of the 4 red marbles, I want to pick any 3 of them. Okay? And because it says or I could either get all 3 coming from the reds, or I can get all 3 coming from the whites. Well, there's only 3 whites to choose from, and I'm going to pick all 3. So before, when we're looking at the stuff from 7.3 and 7.4, that will tell you the total number of ways that you can get 3 marbles from exactly one color. But we're doing the probability now. So what we have to do is divide it by the grand total in general, the most general you can make it. Out of all of these marbles, I need to pick 3. Well, what's all of these marbles? Well, it's 4 red, 3 white, and 2 blue. So 4 and 3 and 2 is 9. So out of just in general, all 9 marbles, then I just need to pick 3. And there's your answer, just like that. Okay. What is the probability that the 2 blue marbles will be among the 3 drawn? Okay. So specifically, what I need to do is I have to get the 2 blue, so a combination of the 2 blue, selecting both of them. That'll tell me how many ways, which is really 1 way, but still. That'll tell me how I can get 2 of the two marbles specifically being the blues. Now I need to get a third marble. Okay, so it's going to be something take one because I need to get one more marble. What is this number going to be? How many can I choose from? Well, it says all I need to do is have for sure 2 blue. We took care of that. It doesn't really matter, so that last one can be either one of the 4 reds or the 3 whites. So together, those are 7 marbles left over. So I'm getting 2, both blue marbles, and then one of the remaining 7 from the red or the white. And then again, divided by the most general of all 9 marbles total, I'm just going to be selecting 3. And there's your answer. Okay, let's go to the next example. In this one right here, what we're doing is we're talking about a probability distribution. So it's spreading out a grand total probability among different groups. If we look at this and analyze it, there are 4 different types of blood types: AB, AB, and O. Okay, and specifically for the percentage of the population, 41% had type A, 12% had type B, 3% had type AB, and 44% had type O blood. So in other words, what is the probability that you're going to, let's say the person that you select is going to have type A blood? Well, if we look along this line, the percentage of the population, it all adds up to a total of 100%, which makes sense. It's got to be a true percentage distribution or probability distribution. So the probability that somebody's going to have like type A blood, well, that meant that there were 41 people out of 100 to give you that 41%. Type B would be 12 people out of 100, then 3 people out of 100, and then 44 out of 100. Okay? And so it's just as simple as that. So what's the probability that someone is type A or type O? Well, type A would be 41 people out of 100, or, so plus, type O is 44 out of 100. So together, 41 and 44 is 85 out of 100, or 85% chance. You have 85% chance of, when you look at all these 100 people, that somebody's going to have either type A or type O, which makes sense. Look up there. Majority of them came from A and O in general. Okay. And by the way, if you're ever doing any kind of probability, if when you do this and you get an answer, if you go and plug them in your calculator and you get an answer, like here, let me go up to this top for just a second. Let me come up in here when we were looking before at these some equaling to 5 and some greater than 8. Notice how it's like 11% or 27%. If you ever get something larger than 100, go back and double check your math. You cannot get anything larger than 100 ever, ever, ever. So you probably did something wrong. So like back to this example right here we were just looking at, if the numerators of those were like 57 and the other one was 44, to where it came out to be like 111 over 100, so it was a lot larger, then I did something wrong, because you can't ever have probability greater than 1, which means percentage greater than 100. Okay. All right, let's wrap this up with one last example. You have a 1 light bulb that's going to be selected at random from 120 light bulbs, and we know that 5% are defective. So what is the probability that the selected light bulb is defective? Okay, what we know is that we have a whole total of 120 light bulbs, okay? And 5% of these are defective. So let's find the number of defective ones. Well, it says that the number of defective bulbs are 5%, so 0.05 of the lot, which is 120. So if we take 0.05 and multiply it by 120, you'll get, that means then there are 6 bad bulbs in the lot. Okay? So the question says, what is the probability that the selected light bulb is defective? Well, how many light bulbs are defective? 6 out of a grand total of how many light bulbs? 120. So if we just take 6 divided by 120 and plug that in our calculator, then we know, again, it just tells you right there, that 0.05. So, but the more important thing is just realizing then, right here, that there are going to be 6 defective light bulbs out of the whole lot of 120. And that right there kind of wraps up the whole lesson on probability.